About variance and standard deviation. Okay, so the standard deviation, so we already know about the mean of a set of data, or the average value, the mean value. The mean value tells us something about the data, but it obviously doesn't tell us everything. For instance, here could be two histograms we could see. Okay, the mean of those two histograms could be is the same. That's what I'm trying to show by the picture, right? In the first histogram, almost all of the data has the value of the mean, or a value close to the mean. But in the second histogram, very little of the data has a value close to the mean. There's a big bunch of the data to the left of the mean that's less than the mean, and there's a big bunch of data that's greater than the mean, right? And so we want to figure out can we get a number that tells us which of these scenarios are we more like? Do we have the data clustered around the mean, or is the data spread out around the mean? And that's what variance and standard deviation are measures of. Okay, the variance is a number used to describe a data set. It gives an impression of how spread out the data is. Okay. So why is this a number we care about? Well, I just explained it helps us figure out how spread out the data is. But the reason why the mean and the variance are the two most important numbers is because it has to do with something called the standard distribution, or the standard normal distribution, and a theorem of mathematics called the central limit theorem. The normal distribution is something you've seen before. It's sometimes called the bell curve or things like that, right? Have you heard of this statement before, the idea of a bell curve? And a bell curve is completely determined by its standard deviation and its mean. So those two numbers completely determine a bell curve. Now, not everything falls under a bell curve, but it's a theorem of mathematics that if you have independent events happening again and again and again and again, what you expect to see is exactly a bell curve in the long run. And so in some sense, that becomes the most important distribution in terms of statistics. And so therefore, we favor these numbers, the mean and the standard deviation. It's easy to understand why the mean is so important, but the variance here and the standard deviation, which is based on the variance, it's not so clear what's going on. So let me show you how you find the variance. If you have a random variable, x, with values xi being taken with probability pi and mean mu, the variance is as follows. And I'll give you a second to catch up with me because this formula is a little bit complicated. Okay, so the values that can be taken are xi, and the mean is the mu. And x takes on value xi with probability pi, and so on and so forth for each of the xi's. Okay, so we want to figure out how spread apart the data is. So we want to figure out, okay, so the first reasonable thing could see says, okay, well, if I want to figure out spread out, I want to see how different x1 is from the mean. And I want to weight that by the probability of x1 happening. That would be the first thing you'd want to think about. I want to figure out how far x1 is from the mean and weight that by how far away, or by how often that occurs. And that'll tell me how x1 is some certain distance from the mean, and this is going to tell us how long we are from that distance. The problem with this approach is that sometimes this number in the parentheses is positive, and sometimes this number in the parentheses is negative. Because if x1 is less than the mean, this number is negative. If x2 is greater than the mean, this number is positive. If we actually did it this way, we would always get 0. So this is not a good way to find how far things are spread apart. What we need to do is we need to always make sure this is a non-negative number, so we square it. And that's how the formula proceeds. x2 minus the mean squared times p2 all the way to the final possible value, let's call it xn, minus the mean value squared times the probability that we take the nth value. That's the variance. Now there's another way to find the variance that you can record, but it's unlikely that you'll need it very often. You find the expected value of the random variable squared, and you subtract the expected value of the random variable quantity squared. It's another way of doing it. So we're going to do this calculation with an example data set in a moment, a simple example of this. That second way that I wrote down that gives you, this should be variance. The second way of finding the variance, we're probably not going to use very often. It's probably, we don't need to remember it very much. We want to be able to use this first one though. Okay, so I'm going to write down a table of values and their probability distribution for a random variable, and we're going to find both the mean and then the variance. Okay, so random variable x has distribution as follows. The values that x can take will be k, and they have the probability that x is equal to k. So it could take value 0 with probability 0.1, value 1 with probability 0.3, value 2 with probability 0.5, and value 3 with the remaining probability 0.1. Okay, so 30% of the time this random variable is equal to 1, 50% of the time this random variable is equal to 2, so on and so forth. So first thing we want to do is find the mean. So we take each value and weight it by its probability. Okay, that's how we find a mean when we have the distribution of a random variable. When we multiply these and add them all together, we get 1.6, right? Which makes sense. We should expect a value between 1 and 2, looking at the table. And in fact, we should expect it to be a little weighted towards the higher number there because of the 0.5 versus the 0.3. Okay, so there's our mean, our mu. Now we can find our variance. The first thing we do is we take the first possible value for the variable, 0. We subtract the mean. We square it, and then we multiply it by its probability. Let's scroll up and look at the formula here. Okay, I'm going to leave the formula here so we see the formula, right? This is x1, this is mu, and this is probability 1. Now I'm going to do that with the remaining 4 values. So this is going to be 1 minus 1.6 squared times 0.3, 2 minus 1.6 squared times 0.5, and 3 minus 1.6 squared times 0.1. All right, multiplying those all, adding them all together, I've done it for us here. This turns out to be 0.64. So 0.64 is the variance of this random variable. Now, I mentioned there's another quantity that's important called the standard deviation. The standard deviation and the variance and the standard deviation are both measures of spread. So the standard deviation of a random variable, x, is defined as, we call it sigma and a little x down here, It's the square root of the variance. Right. So remember, each time when we found the variance, we took the difference of the values of the random variable from the mean, but we squared them in order to get something non-negative, in order to get something that was positive. This is kind of undoing the square. This is not technically what's happened, but this brings us back down to the right units. Okay. So with the standard deviation, we can make a statement like follows. We expect 65% of the outcomes to be within one standard deviation of the mean. And actually, I think it's 68% normally. This is for normally distributed things, which we're not going to talk about. But these statements that we make about standard deviations, we make them like this, right? We say, okay, we expect 68% of the people to be within one standard deviation of the mean. Okay. This is true for things like adult height of men or adult height of women. And looking at that, and we find a mean, and 2/3 of the people will fall either at the mean or between the mean. 2/3 of people will fall between the mean minus the standard deviation and the mean plus the standard deviation. So when we're adding, in order to compare a mean and a variance, we can't really do it because the variance squared things, it's the wrong units. So to get back to the right units, you use the standard deviation. So this is just, we're not going deeper into statistics. If we were, this would be important to get used to the difference between the two. But this is the final section that we're doing on statistics. So there's not that much more to say about this other than the standard deviation is in the right units. Okay. Now, for binomial random variables, we have an easy formula for standard deviation and variance. I'm gonna put the expected value again. So this would be, let's say n trials. P is the probability of success. Q is the probability of failure. The expected value or the expected number of successes we learned on Monday was n times p. It's the expected number of successes. The variance that we expect to find is n times p times q. I'm just handing you these formulas like Moses. These can all be derived, but for now we're just going to write them down, right? And this is square root of n times p times q then, because the standard deviation is just the square root of the variance. Okay. So we're going to do an example with a binomial random variable to see what I mean by the mean and the variance. So let's compute the mean and the standard deviation for the number of ones appearing on 180 rolls of a 6-sided die. So we're going to compute the mean and the standard deviation, and then we'll have a statement about what's going on here. So the number of trials here is 180. The probability of success is 1/6, because only 1/6 of the time we'll get a 1. And the probability of failure, therefore, is 5/6. So the mean, which is the expected value, is 180 times 1/6. So we expect to get 31s. But of course, if you've done this in real life, you would probably not get 31s. You would not get exactly 31s. It's not likely. It's more likely than not that you won't get exactly 31s. Right? But you'll get a number near 30 is the idea. So the standard deviation is going to be the square root of 180 times 1/6 times 5/6. Because this is n, this is p, and this is q. When we compute that with a calculator, well, we don't even need a calculator. When we compute this, we actually get 25. Square root of 25 is 5. So what we can say here is that the mean is 30, but the standard deviation is 5. So we should expect to get 30, but we expect to vary from 30 by about 5. And the actual statement here that has to do with the central limit theorem is that we have a 68% chance, basically, not exactly, but this is estimated, of getting between 25 and 35 ones. And we have a 95% chance of getting between 20 and 40 ones. Right? So the standard deviation, there's something called the 68, 95, 99.7 rule. And basically, if you're doing something that has a lot of independent outcomes again and again and again, like these binomial trials, then 68% of the time you're within one standard deviation. 95% of the time we're within two standard deviations. And 99.7% of the time you're within three standard deviations. So it'd be very rare to get, okay, so for this problem, this would be between 25 and 35 ones. This would be between 20 and 30 ones. And this would be between 20 and 40. This would be between 15 and 45. So to get more than 45 ones on 180 rolls of the die is a very rare occurrence. It can happen, but it's very rare. But to get between 20 and 40 ones is quite common. Right? That'll happen 19 times out of 20, 95%. So this is why the standard deviation is useful as a rule of thumb. It can allow you to quickly compute what are the broad ranges of things you expect. Right? Business obviously involves risk, right? And so you want to somehow quantify risk and think about how good or bad the risk you are taking could be. And the standard deviation and the mean are a good rule of thumb for estimating these risks, right? These are just estimates. But there's a mathematical theory that says that if you keep playing these games forever, these things converge to these estimates. And that's the central limit theorem of probability. Okay, one more thing that's a little bit complicated, but I need to cover here in the last few minutes, is when we don't talk about probability distributions, but rather samples from a larger population, the formula for the variance changes. So first I'll write down the formula for the mean. Okay, if the sample that I get is, say, x1, x2 through xn, these are the values I get for my sample. The mean is what you'd expect. We add all the values in the sample, and we divide by n. That's the mean that we get. The variance is different. We're going to call it s squared. The variance is the standard deviation squared. So really the s is being defined here. We take the first outcome minus the mean and square it. The second outcome minus the mean and square it, all the way to the nth sample minus the mean and square it. Now, if we were just doing what we did before, all of these have probability 1 over n, because they all occurred once. So we divide by n. But actually, for very technical reasons, we divide by n minus 1 instead. So when you find the variance from a sample of 100, you divide by 99. Now that's not going to make that much difference. Dividing a number by 100 versus dividing a number by 99 is usually not going to make that much difference in the number. But with small samples, it makes a difference. Okay, why is this n minus 1 here? Well, it's a technical problem, and it has to do with the fact that this mean that we calculated is probably not the true mean. Right? It's a sample mean. It's probably off by the true mean by a certain amount. And this n minus 1 there is supposed to capture that certain amount. And in some theoretical sense, you can show that it does. But you don't need to worry about that. You just need to remember when you're computing a variance from a sample, you divide by n minus 1, not n. So if you are given the probability distribution to find the variance, it's dividing by n. But when you are given a sample, it's divided by n minus 1. It's a little bit strange, but it's the reality. And then s is the standard deviation. We take the square root of the variance. That's the same thing. That doesn't change. Okay, the homework for Friday is going to be 4, 6, 8, 10, and 12. Just 5 problems for you. Okay, 4, 6, 8, 10, and 12. There will be a quiz on some stuff from section 7.2, 7.3, and 7.4 on Friday. All right.